Can you give an example how model calibration might be useful in a real world scenario?
Sure. Basically, we are going to take medical diagnosing medical condition based on patient reports example. So if a model is not well calibrated, it might provide prediction with high confidence, even when it's not when it's very unsure about their predictions. So this could lead to incorrect diagnosis, and collaborating the model basically ensures that it provides probabilities that accurately reflects its level of certainty.
Fair enough. Also, during the slides, you said that calibration helps reduce biases. Can you explain this point more in detail?
Basically, biases can occur when a model is consistently leaning towards one prediction, even when the evidence doesn't support it. Basically, calibration helps by aligning the model prediction with real world outcomes. For example, if a sentiment analysis model is biased toward positive sentiments, so it might incorrectly label negative comments as positive as well. So, model calibration basically correct the bias, making the model more balanced and fair in its prediction. And the biasness always due to the training of the model, like pre-training of the model.
Ladies and gentlemen, welcome to another very good lecture in the course of LLMS. This lecture is called Model Calibration in LLMS. And also, we have requested our AI expert, Ms. Nisa, to, to join us and describe the whole context in detail. I welcome you, Ms. Meher, on the call,
Thank you so
and
much, sir.
if you can kindly elaborate more on the model calibration, it will be nice. Thank you. Over to you.
Thank you so much. Assalamu alaikum, everyone. I hope you are doing well. So we will discussing about model calibration and large language model and why it is important. So let's break it down. So in this presentation, we will start by explaining what model calibration is and why it's a big deal, especially for these large language models. So we will be even show you a real example to make it crystal clear, and we will then talk about how calibration can affect things. Plus, we will explore two ways to do it. One, the that doesn't require much technical knowledge, and how one that's more technical and called which is called as contextual calibration. So what is calibration? Imagine you have a weather app on your phone, and sometimes it tells you that it's 30 degrees Celsius when actually it's 25 degrees Celsius. That's not very helpful, right? So calibration is like teaching the app to be more accurate. It's about making sure that the model prediction matches what happens in the real world. So that's very crucial, especially for LLMs, because sometimes they can be a bit too overconfident in their answers. So let's pick an example. Let's put it in a perspective of a temperature again. So a well-calibrated model would say it's around 20.5 degrees Celsius when it's actually is 21 degrees Celsius, matlab really close. But a model that isn't calibrated might say it's 15 degrees Celsius, way off the mark. So this is the difference between a calibrated and non-calibrated model. So you have to tune it to make them calibrated and match real-world scenarios. So as now LLM are solving every traditional ML machine learning task possible, like classification, clustering, labeling, even data creation and generation as well. So it's very important now to understand these issues that we might face in this scenarios, and how we will tackle them. Understanding the graph of calibration curve. So if the graph is a straight line with a slope of 1, the model is perfectly calibrated. And if it's above the line, the model is too confident, like thinking it's always right. So it's always and if it's below, it's not confident enough. So like being unsure about its answer. So we need for a good calibrated model, we need the line to be somewhere around in the in the slope with a straight line. It cannot be a full straight line always with LLMs, but we actually need an approximate straight line in this case. So why do we calibrate models? So in simple words, calibration is a bunch of ways. Basically, it makes the model it makes the model's prediction more reliable, easier to understand, and even better for decision making. Plus it reduces those annoying biases that we might face in models that basically mimics their training data sets. So we will going to be taking an example which we all know and we have all have discussed in customization of LLM first part, which was fine tuning. So we have discussed in that lecture that how do we do sentiment analysis with LLM. So we can do a lot of things like question and answering, sentiment analysis, conversational. So sentiment analysis is one thing that basically predicts a label, which was being used which was being done by traditional models, and now this place is basically taken by LLMs. So let's play this to something practical, like that's when we figure out if a text is positive, negative, or neutral. So LLM can do this, but sometimes they are too sure about of themselves, and they can lead to wrong conclusions as well. So with the demanding interest in LLMs, we need to address this issue as well. So now let's take an example here. So what exactly does it mean to calibrate an output distribution? So we learned about output distribution in the components of transformer lecture. Imagine we are teaching our model to predict sentiments, whether a model is positive or negative, but sometimes the model gets something with no context at all, like input is equals to nothing sentiment. So we call this a context free input, where the model don't have anything to predict from. So now here's the thing. Since nothing doesn't lean towards either positive or negative, so we would expect the model to say it's 50-50, right? Both positive and negative should have a 50% chance. But surprise, that's not the case with LLMs. They basically predict very biased outputs, and well, these probabilities are leaning towards like heavily towards positive sides, because in LLMs for some reason the biasness is always towards the positive end. So it means that the model might end up thinking everything is positive even if it's not. So that's where the calibration steps in, and it helps us balance out things. So a non-technical solution, it's basically straightforward. Imagine you are teaching a kid by showing examples. So in this case, you would give the model some examples that are clearly that basically clearly shows that the input is equals to nothing sentiment can be both positive and negative as well. So in the image, you can see that the user is basically inputting a series of examples. This is also called few shot learning as well. We have learned it in previous lecture as well. So we are giving basically some examples to tackle this situation very temporarily. So we are saying, look, sometimes it's just one, sometimes it's the other. So it's simple solution, but it's not widely explored yet. So we are not entirely sure how well it's going to work in practice. But for a quick fix and a temporary solution, you can just provide the model with a few examples, and it might help you to basically make the output more better. Now moving towards the technical solution. So the technical side is contextual calibration. So this is like fine tuning a guitar string by string. So here we are adjusting special settings called calibration parameters. So they have a proper calibration parameters that are designed for this task. So to ensure that context-free input, like input is equals to nothing sentiment, gets a fair 50-50 chance of both positive and negative. And to make it clearer, let's walk through an example of how we compute these calibration parameters. So remember the example where the model gave these probabilities of zero point 0.9 and zero point 0.1, like far from zero point 0.5 neutral range. So we want to adjust these so that it's 50-50 for both positive and negative. So we do this by creating a mathematical transformation. And in this case, we have this equation, which is Q is equals to softmax WP plus B. So here Q is our new probabilities, W and B are our calibration parameters that we want to adjust. We are essentially reshaping the original probabilities P to be more balanced. But how do we calculate W and P? It might look a bit strange, but it's very simple solution. It's about taking the inverse of the original probability. So it's like, hey, just flip these numbers around to make the things even. So you just have to take inverse of this equation, and then you will get a balanced equation. So it doesn't make any sense, but it works, and it is practically proven that it handles the calibration very effectively. Another method that is basically specific to generation of generation of language. For now, we are talking about classification thing, but if, in generation we face calibration non-calibrated examples as well. So we can take B to the inverse of P minus. And W can be the identity matrix. So in this way, this method works better for some tasks, especially when you are creating stuff instead of classifying things. Now, here another aspect. So now you must be wondering that how we know the bias, like how do we know that our data set, our model is biased, or what are the biases that are causing this non calibrated problems in our model. So when we are working on calibration, we essentially fine tune our model to be as accurate as possible. But here's the thing, if we only use the same old data to train and test our model, it's like practicing a same song with the same progression over and over. So you will get the get you will be get like a really good at that one song. But what if you need to play something different? So you will not be comfortable with that. So that's where the holdout data set comes in place. So there's another separate data set, like we all know about training data set, testing data set, validation data sets. This is different from all these data set. This especially for calibration to pick biases from the model. And basically it's like a a fresh set of a set of nodes. So we don't use it during training. It's completely separate. It's this data set helps us evaluate how well our model can perform on new unseen data. So it's like having a test audience listen to your music before a very big concert. Now some takeaways. So I'm going to say just one thing, one sentence here. So remember these key points. Calibration is super important, and there are different ways to do it. The one you choose depends on what you're working on. So it highly depends on your specific example. They are very specific to the data set you are working with. So that's all from calibrations. If you have any questions, you can ask.
Thank you very much. That was a very fantastic lecture on model calibration. I have few questions on the model calibration. Let me ask them. Yeah. So, can you give an example how model calibration might be useful in a real world scenario?
Sure. So basically we are going to take medical diagnosing medical condition based on patient reports example. So if a model is not well calibrated, it might provide prediction with high confidence even when it's not when it's very unsure about their predictions. So this could lead to incorrect diagnosis, and collaborating the model basically ensures that it provides probabilities that accurately reflects its level of certainty, making it very safer tool for medical professionals, because we know that LLMs is will going to be more efficient in these tasks. So we have to address these issues as well.
Okay, fair enough. Also, during the slides, you said that calibration helps reduce biases. Can you explain this point more in detail?
Basically, biases can occur when a model is consistently leaning towards one prediction, even when the evidence doesn't support it. Basically, calibration helps by aligning the model prediction with real world outcomes. For example, if a sentiment analysis model is biased toward positive sentiments, so it might incorrectly label negative comments as positive as well. So, model calibration basically correct the bias, making the model more balanced and fair in its prediction. And the biasness always due to the training of the model, like pre-training of the model, and not because of the fine tuning, but you can basically tackle it in the fine tuning stage, which is basically model calibration.
I see. I see. Okay. You also mentioned a non-technical solution and a technical solution for calibration. Can you discuss which one is better to use over the other one in practice?
Yes. So the choice between two often depend on your specific application and available resources as well. So a non-technical solution which involves providing example, it's basically simpler to implement, but may require a larger and a very good labeled data to basically do that, because it's few short learning. So on the other hand, the technical solution like contextual collaboration might be preferred when you have fewer labeled samples, or you when you need more fine-grained control over a calibration process. So it's just a trade-off between simplicity and control. But whenever you are just looking for a temporary fix, you just first try to solve it with a non-technical solution. And if the bias is not that much strong, or all over the data set, then it can be fixed with a temporary solution as well. But if the bias is basically showing in the explanation side of model as well, so that's when you need to basically implement a technical solution, and to do it basically with contextual calibration.
Okay, okay, I see. One more thing that you mentioned about the holdout data set. So how we ensure that holdout data set is a representative of the real world and it is not going to uh, introduce biases of its own?
Yes, that's a very big issue with holdout data sets, because sometimes they are very much alike training data sets, so they don't do anything. So basically, it's very crucial to select a very good holdout data sets. One way to do this is by carefully selecting data from a wide range of sources and scenarios that your model is likely to encounter in real world. So it's also essential to keep the holdout data separate from training data to avoid any mixing with that, and regularly updating the holdout data set to reflect changes in real world data can help basically maintain its representation. But if you ask me about how I will tackle this issue, I would recommend just taking the context free instances in holdout data set that you that will just help you just by looking at the prediction of model, you would know that this is some biasness going on. So that's how you basically choose a holdout data sets.
I see. Also, you mentioned in your lecture contextual calibration, which involves suggesting calibration parameters. How often should these parameters be updated in a real world application?
Basically, the frequency depends on the nature of application and the stability of the model prediction. So, in some cases, you might update them regularly, especially if the data distribution shift over time, because sometimes it's just something very common, and sometimes it's very technical. So, for other applications, for or a one-time calibration might just enough if the model prediction remains stable. So it's essential to monitor the model's performance and recalibrate as needed to maintain the desired accuracy of it.
Sure, sure. Thank you very much. That was a very wonderful lecture, Miss Mehrun. And I'm
Thank
very
you so
thankful
much.
to you for giving us time. Ladies and gentlemen, thank you very much for watching this video. And